This is one of the hardest questions I've seen in all the A-level maths past papers. Now, unfortunately, in maths exams, there probably will be that one A-star question where it doesn't matter how much revision you do, it doesn't matter how many past papers you do, you just won't get it. Unless you're an A-star genius and you're going to do maths or physics at university, these kind of questions sometimes you just won't get. Now, the question I'm going to show you today came up from an AQA past paper. I haven't seen anything like this in an Edexcel past paper, so warning, if you do Edexcel, you may want to pay attention because they have not asked a question like this yet, but AQA have. But regardless, just save this video anyway. Doesn't matter what example you do, just save it. Now, to understand this question, there are two topics that you need to have seen in class. So small angle approximations, right? So the sine small angle approximation, the cos one, and also radians, okay? So if you've seen those two topics, you will understand this. If you've not, again, save this later and you can come back to it. Now, it is a three-part question. The first two parts, part A and part B, are not too bad. If you know your small angle approximations and radians, you should be fine with the first two parts. It's part C that is the tricky one. So again, do stick with me with this video. So part A, show that for small values of x in radians, show that this trigonometric function is about 9x cubed. So this is where the small angle approximations come in. Now, they do give you some in the formula book. So in the formula book, they give you that when x is small and in radians, sine x is about x and cos x is about 1 minus x squared over 2. Now, obviously, what you'll notice with this one, okay, is we have sine 2x and cos 3x. We don't have single x's. We have a double x there and there, and we have a triple x with the cos. So remember what you do with this, okay? So the idea is that if you do have a multiple of x inside your angle, that means you just times that x there for the sine one. With the cos one, when you have a multiple of x inside the angle, you've got to times this x by a, but you're squaring the entire thing. Because remember, it's like with functions, right? When you plug values into functions, you have to plug in that entire value into that squared function there. So those are your approximations that we're going to need with this question. So again, obviously in this case, we got sine 2x. So that a really should be 2 with this question. So that's going to be a 2 there. And we have, again, sine 2x there, but cos 3x. This a there is going to be 3 with the cos. So 3 and then 3 inside there. So what we have then is sine 2x, which is approximately 2x, as we just said before. And then minus sine. And then again, another 2x, so approximately 2x. And then multiplied by cos 3x, which is approximately 1 minus 3x all squared. So here, 1 minus, and then 3x all squared over 2. So like that. So we've got 2x there, obviously 1 here. And then we've got 3x all squared. That's going to be a 9x squared, right? So 9x squared over 2 with this one. So now we can go ahead and expand some brackets like this. We got 2x, take away 2x, minus 2x times minus 9 over 2x squared. That is going to be positive because the minus signs cancel out. The 2's cancel out as well. 2 over 2 is 1. So we've got plus 9x cubed. Okay, so now the 2x's cancel out and we're left with exactly what we needed, which was 9x cubed with this question there. So now moving on to part B. So part B is hence show that this integral, so an integral from 0 to 0.1 of exactly the same trig function as before, show that this integral is about 9 over 40,000. Now with these questions and with most of these A-level maths questions, there is a reason why they made you do part A. And that's because part A is supposed to help you out with this question here. So now we know that when this x value or the x value in these angles here is small, we can use small angle approximations. Luckily, we're integrating with small x values, okay? So small x values in radians. So that means because these x values in the limit are small, we can use the small angle approximation that we used before. So when the x value is small, again, we know that this thing is about 9x cubed, right? So this integral from 0 to 0.1, again, the limits aren't changing. We're still integrating along the x-axis. It's going to be here 9x cubed now with respect to x. So you know from first year how to integrate things like this, right? Add 1 to the power, divide by the new power. So we're going to get 9x to the power 4, divide by 4. Limits are 0 to 0.1. So you plug in 0.1 into this, you plug in 0, you subtract them from each other. So you get something like this. Now obviously this second one is just 0, right? 0 to the power 4, 0. And then you got this here. When you simplify this, I promise you, you'll get this there, right? So this will turn out to be 9 over 40,000 as we need. Oh no, sorry, I put an extra 0 there, sorry. 9 over 40,000, yeah, 4 zeros, so that's our answer. So now this is the one that I really want to talk about, this part C here. Determine the values of A and B such that this integral is about this integral here. Now firstly, notice how on the left side, this is exactly the same as part A and part B, right? So nothing has changed inside the integral, or the integrand as it should be called. But the thing that's changed compared with this part B is that now the limits are 12.6 and 12.7. So we've got quite big limits here compared with these smaller ones. And we want to show, or we want to find the A and B values that make this integral approximately this one. Now we know that for small angles, when this x value is small, we know that this thing is approximately this thing, right? So if x is small, then this thing is about this thing, 9x cubed. The problem with this question is that we're integrating with x values that are not very small. These are quite big, aren't they? So you can't just say that this integral is about the integral from 12.6 to 12.7. So A can't be 12.6, B can't be 12.7, because these are not small x values. So that's why this one is tricky. So again, we know that this integral cannot be approximately this one, because again, we're not dealing with small angles. So this cannot be about this. So what do we need to do with these limits here? Let's think about what we have here in more detail. Now, to investigate this further, we need to really think about what types of curves we have here. So this is a sine function, and sine functions are waves. So that is a wave. The same with this here, okay? Sine 2x, again, the same thing. It is a wave. The same with this here. This cos 3x is a wave. Cos and sine graphs are waves. Now, if you have done any kind of physics, you will know that if you add two waves together, or if you subtract two waves together, you create a new wave, right? So one wave plus another, or one wave take away another, you get a new wave, right? It's called superposition of waves. So when you add waves, you create waves. And also when you multiply waves, you create waves as well. So this thing in speech marks is a wave. We have a wave, take away the product of two waves. Two waves times together is a wave. Wave take away wave is a wave. This entire function is another wave function. Now, what do we know about waves? Well, waves have an amplitude, and they also have a period, because waves are periodic, they repeat. So, you know, if you have a wave like this, right, the wave is repeating. So from here to here, the wave repeats. So from there to there, again, the wave repeats. So we have a period of the wave, the time period that it takes to repeat, and obviously the amplitude. So if a wave repeats, then that means the areas repeat. So for example, I know that this area there must be the same as this area there, because it's the same wave, right? I know that area looks a bit bigger, but it's supposed to be the same wave. So area there, area there. So what we can kind of realize is that integration is obviously finding areas under curves. So this area must be the same as a kind of transformed area backwards to smaller x values. So I need to know the period of this wave. I need to know when the wave repeats, what time it takes for the wave to repeat. Now we should know that sine x and cos x repeat every 2 pi radians, so 360 degrees in degrees, right? Because we're dealing with radians with integration, we've got to use radians. So sine and cos waves repeat every 2 pi radians. Now, obviously with this question, we have a 2x and a 3x in the angles instead. So when does the graph y equals sine 2x repeat, right? So if you put the 2 inside the function, remember graph transformations, you're going to stretch in the x direction by a factor of 1 over 2. So you actually squish the graph in. So this graph is going to repeat not every 2 pi radians, but half it every pi radians. Because again, with this graph, you squish it in by 2. So it repeats every pi radians instead of 2 pi radians. So again, we know that these sine 2x's repeat every pi radians. What about this cos 3x? So cos 3x is going to repeat every 2 pi over 3 radians. Why is that? Well, a cos graph repeats every 2 pi radians. When you put the 3 inside the function, so f of 3x, you squish the graph in by a factor of 3 parallel to the x-axis. So the period is going to be 2 pi divided by 3 because you third all the x values. So this is going to be your period for this cos 3x. So we've got a situation here where this wave repeats every pi radians, this wave repeats every pi radians, but this wave repeats every 2 pi over 3 radians. So we've got to think about lowest common multiples a little bit with this. So if sine 2x repeats every pi radians, then of course it repeats every pi radians, but it also repeats every 2 pi radians, every 3 pi radians, every 4 pi radians, right? Just the multiples of pi. Let's do a similar thing with the cos 3x. So cos 3x repeats every 2 pi over 3 radians. Now double it. So double that, you get 4 pi over 3. Treble that, you get 6 pi over 3. Times that by 4. So now we're going to get 8 pi over 3, right? So this cos wave is going to repeat every lot of these radians here. Now let's just simplify this fraction here that we see here. That there is going to be 2 pi. We have a lowest common multiple. So the sine 2x wave repeats every 2 pi radians, and so does this cos 3x graph. It also repeats every 2 pi radians. So that tells us that this wave repeats every 2 pi radians. So that means if you have this wave, so again, this wave in the integral, and it's repeating every 2 pi along the x-axis, it means the area is also repeating every 2 pi. So this integral is going to be the same when you add 2 pi to the limits, or when you add another 2 pi to both limits, or when you subtract 2 pi from both limits. The areas are not going to change. So again, just to be clear, this area is the same as this area. The dot 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 just means everything inside there. I'm lazy, I can't be bothered to write everything out again. But the integral is the same when you add 2 pi radians to the limits. Also when you add another 2 pi, another 2 pi, and also when you subtract 2 pi radians, okay? So again, if you take away 2 pi, the area is still the same. If you take away another 2 pi, let's just take away another 2 pi here, right? 2 pi there, 2 pi there. Again, the areas are not changing because the wave is repeating every 2 pi. So in a very long-winded way, what I'm trying to tell you is this. With this question, we are using the small angle approximation to approximate this original thing, right? If we are going to use that small angle approximation, then we need to make sure that this A and B are small. And the way that we make sure that this A and B are small is by basically taking away 2 pi until we get small limits, because now we know this thing repeats itself every 2 pi along the x-axis. So I mean, you can literally just do this 12.6 take away 2 pi, see if it's small. Now 12.6 take away 2 pi is 6.3, not really small. Let's take away another 2 pi. So answer, take away 2 pi. Now this is pretty small, isn't it, right? So 0.0336, this is pretty damn small. So what that's telling me is it's telling me that this A must be 12.6 take away 4 pi. So we have, let's just get rid of this there, we don't need that. So we've got here 12.6 take away 4 pi, because we had to take away 2 lots of these 2 pi's. Do the same on the top. 12.7, remember that's our top limit, 12.7 take away 4 pi. That integral of this 9x cubed is going to be approximately the same as the original trig integral, right? So this sine 2x take away sine 2x, going to run out of room here, but this integral here that we saw before, dx. So yeah, your final answer for A is this. That is your A there, and that there is your B. is a tricky one. It is an A-star question. So if you do have any comments or questions, just let me know.